Hi, this work example is on logistic regression, and I'm going to illustrate how to use stat tools to do logistic regression. And the example that I'll be using is problem number 1 in the textbook, chapter 17, so that's on page 558. So please bring up the file, and you will see it. The file name is P17_01. And you will see this this file. Okay, so this is a record kept by a beer company to see whether a customer will like regular beer or light beer, and the properties that are being tracked are gender, what the marital status, income, and age. So you can see that the gender and marital status are already turned into a dummy variable. So if you recall from the book that the stat tools logistic regression requires the dummy variables to be constructed beforehand. So not like the regression tool that will actually allows you to construct the dummy variable as a by changing the type of the independent variables. Here, for whatever reason, the logistic regression tools within stat tools requires you to change to construct the dummy variable already. So basically, you change that to 0 and 1. So you're building the dummy variable yourself. So of course, whenever you build a dummy variable, you have to remember what's the base and what is the actual the dummy variable when it's 1. So in this case, gender, when it's 0, then it's female. When it's 1, it's male. So the base case is female, and the 1 case is male. And the marital status, 0 is not married, and 1 is married. Okay, so in order to use that, in order to use this logistic regression tool in stat tools, then you have to we'll have to also turn the dependent variable into a 0 and 1 also. So it doesn't really take the simple categorical variable like this regular and light. We also have to turn this into zeros and 1. Well, that part, the reason is a little simpler because essentially the output of a logistic regression is a percentage as probability. So basically probability is between 0 and 1. And so when you see the probability, you can actually easily interpret that to whether it's closer to 0 or closer to 1. So when you turn the dependent variable into a 0 and 1 binary variable. So in order to do that, we just have to introduce let me just call it preference regular. So I'm going to turn all the regulars into 1 and light into 0. So it's a simple if formula, and just have to check whether column F is regular or not. And if it's regular, then I'm going to put a 1 here. If it's not regular, then I'm going to put a 0 here. Okay, I'm going to press enter. And then if I want to fill up the whole table, all I have to do is just double click at that little handle at the bottom right hand corner, and then it fills up everything. Okay, so now I can start my logistic regression. So I just have to declare the data set. So I'm going to go and declare this data set, and I'm just going to click OK, and then I can start the logistic regression. So I'm going to go here and then start the logistic regression, and then I'll have to select the dependent variable and independent variable. The dependent variable is the last one, the preference regular, and the independent variable, as the book told us to do, it's married, income, age, and beer and gender. Sorry, I missed the first one. And I just want to include the classification result and there's the last one you can't check because there's no prediction. Okay, so I'll show you why the last one is useful. So later. So I'm gonna click OK. Then I will be able to see the result of the prediction. So you see that the result is showing right up here. So let's look at the result a little bit. Um, let's first look at the classification matrix. So the classification matrix is sometimes called the confusion matrix. Actually, in all data mining world, it's called confusion matrix. So this is this cell is true positive. This cell is false positive. This one is false negative, and this one, the last one, is true negative. So if you want to calculate, you can actually calculate the precision, specificity, and the sensitivity. But we're not doing that here. We just want to see the result. Take a look at the result a little bit. So the result actually looks not bad. The percentage correct is 88% for both the 1 and 0. So you can imagine that if you add them all up, then there's a total of 100 data points, and then if you add them all up, that's so 88 data points were right, and 12 data points were predicted wrong. So the percentage correct is 88%. So that's really not that bad. But the interesting thing also to look at is the bottom. So the base case is 50%, meaning that we just predict random the random preference. So if the 50% of the people like light beer and 50% of the people like regular beer, that's actually the average of the data points. And the correct prediction is 88%. So that's actually a 76% improvement over 50%. You can calculate that. It's 88 minus 50 divided by 50, so that's 76%. So it's a much better. It's actually the prediction is a much better way to distinguish whether somebody likes light beer or regular beer versus just using the average, because it turns out the average that is 50% light beer and 50% regular beer. And let's also take a look at the coefficients. So you see that the coefficient for gender is positive, for married is negative, for income is negative, and for age is positive. So that means that the probability of somebody who might like regular beer increases when it's a male, because remember 0 is female, 1 is male, is not married, and the income is lower, and also when this person is older. So an older person tends to like regular beer, and people with less income tend to like regular beer as opposed to light beer. And finally, let's take a look at the column E, the p-value. Well, we didn't cover chapter 11 after the regression, so we didn't really cover the statistical part of it. So this all-important p-value was really not discussed. But here, let me just mention a little bit what the p-value means. Well, p-value is essentially the prediction for this particular coefficient. So the significance of the prediction for this particular coefficient. P-value should be lower, as low as possible. So lower p-value means that this particular coefficient has higher prediction power. So usually we're looking for p-value less than 0.05, and for p-value higher than 0.05 or even 0.1, we usually discard. That means that that particular factor or coefficient is not really relevant to the prediction. So in this case, you see that for gender, the p-value is over actually 25%. It's over 0.27. And married is even higher, which means that these two values, or these two factors are really not that useful in predicting somebody's preference for regular beer or light beer. So when you actually do a correct, when you actually want to do a regression, then you usually want to go ahead and discard those two. So get rid of gender and married from the independent variable lists, and then we can actually probably will be able to make a pretty good prediction still. So let's do that. Okay, let's see if what happened if we only use income and age, because gender and married don't seem to have predictive power. So let's go back to the data, and then we do another logistic regression. So this one is going to be the same, except that we're going to get rid of gender and married. And then I'm going to say OK, and then see if we will create a good result. In fact, if you look at this, then the prediction is the prediction power seems to drop a little bit, because compared to the other one, the ones for the confusion matrix for the true ones, which is still 88%. For the true zeros, or for the light beer drinkers, now dropped from 88% to 84%, but it's really a minimal drop. So which means that after you drop those two factors from the independent variable list, the predictive power of this logistic regression doesn't really change by much. So when you see something like this, then you will want to keep the minimum number of independent variables, because when you actually include too many independent variables with high p-values, or with little predictive power, although you can probably improve the result a little bit, but when you actually make predictions, because there's the likelihood of high correlation among those useless independent variables, which of course we didn't discuss because it was covered in chapter 11, then actually it will create problems when we try to make predictions with new data sets. So we're going to use this one. I'm going to keep this one instead of the previous one that includes pretty much everything. Okay, so now let's see the second part of this problem. So the second part says we consider a new customer as a male, married, income with $42,000, and age 47. Can we predict whether this person will like regular beer or light beer? Well, there are a couple of ways to do that. The easiest way to do that is just to put that person right on this sheet, right on the result sheet, right? So we can either use the previous one, or we can use the new one. Let's actually use the previous one, because we already have all of the data. Then we can compare the result. Okay, so now let's add this person. So this is, we'll do a prediction. Okay, so I'm just going to add a prediction. And then this person, so the constant is always there. So this is, remember, we're trying to reconstruct the probability. So the probability in the textbook was expressed as probability of somebody who will show the result 1 is 1 over 1 plus e to the minus of the regression equation power, right? So we want to add those factors in here. So the constant, of course, always have the 1 here, and the gender is male, so male is 1, right? And the married is 1, and then the income is $42,000, and the age is 47. Okay, so what can we do? What can we predict as a probability for this beer drinker? Well, we just have to enter the formula. So its probability is 1 over 1 plus e to the minus the whole regression power, right? equation power. So this is what we're gonna do. So we're gonna do the 1 minus. So this is the probability that we're calculating. 1 over 1 plus exponential. So it's minus, and then we have to reconstruct the whole regression equation. So the regression equation, actually, I don't need the last parentheses. So it's a sum product of the coefficient and and this person's numbers, right? So we've done this a couple times, so you should remember that this is exactly how it works. So I'm gonna add all of the parentheses back, and I press enter. Then this is the probability. So the probability for this person to be a regular drinker is 0.579, okay, or 0.58 actually, because if I do the if I round it up to two decimal places, and that's 0.58. We can also do it here. So all I have to do is to only put in the constant, which is 1, and then the income is 42,000, and the age is 47, and then I'm gonna produce the exact same formula, which is 1 plus exponential minus sum product, all the coefficients multiply by the actual value for this person, and then it's a little lower actually. So if we only use the income and age, it's a little lower, but it's still over 50%. So if you use 50% as the cutoff, or yeah, if you use the 50% as the cutoff, then both method or both regression, one with every single factors and the other one with only income and age, both would give you the same result, that this person is likely to be a regular beer drinker. Another way to do that is a little more interesting. So let me show you how this will work. So I want to construct a prediction set, so that actually after I perform after I perform this linear regression, then the logistic regression will actually make a prediction for the new data set. So the new data set is a data set with unknown independent variable. So let me build one. I need the heading. So I'm going to copy the heading. So I'm going to put it at the bottom right here. Okay, and then I'm going to put in the individual number, which is 101. The gender is male, remember, so it's 1. And the married is 1, because yeah, it's 1. The income is 42,000, and the age is 47. Okay, and I'm gonna leave the last two blank because those are unknown. So I want to use the logistic regression to predict whether this person is a beer drinker, is a regular beer drinker or a light beer drinker. So the first thing I need to do is to declare this as a data set. So I'm going to have to declare this part as a new data set. Okay, so that's cool. And then I am going to perform my logistic regression again. So I'm going to do the logistic regression with only these two independent variables, and the preference regular as the dependent variable. But this time I'm going to include a prediction. So the prediction will be performed on dataset 2. Remember, dataset 2 only has one person in it. So now if I say OK, then you'll ask whether all these matching dependent variable will be overwritten. Do you want to do that? Yes. Okay, because I didn't have any. So now I produce exactly the same. See, when you check the linear regression result, the logistic regression result 2 and 3, they look exactly the same. Okay, but if I go back to the data set, then the prediction is inserted here. So I can actually add a new data set, and then have the stat tools make the prediction based on the result. So this is another way to actually directly get the prediction result. Remember, in data mining, usually we break the data data set down to both into a training set and a testing set. Logistic regression routine in StatTool doesn't do that. If you want to do that, you have to break it down yourself. So you have to partition the 100 data points into let's say 85 or 80 data points as training set, and then you use the other one, the other set, the remaining 20 as the testing set, and then you can do the prediction and compare the predicted result versus the actual result, and then you can see the accuracy of this logistic regression based on that. But also you can just collect new data for people based on the gender, marital status, income, and age, and then make a prediction using the logistic regression model that you just built based on the 100 data points, and make predictions for other data, for any new data that you have. And then you can do that right within you can do that in the using the mathematical calculation, just like I did on the regression result page, or you can just add a testing data set or the prediction data set, so that the logistic regression will actually make the prediction for you automatically, so that you don't have to do that calculation. Oh, by the way, the prediction is actually made exactly as we did. So what the StatTools did was just basically take all the coefficients, put these numbers into the logistic regression equation, calculates the probability, and then will post 1 if the probability is higher than 50, and 0 if the probability is lower than 50. So that's all you did with the when you ask StatTools to actually make predictions when you start the logistic regression.